Right. So let us start with the tensor. I'll write the definition of a tensor. A set of quantities t primes. So tensors. A set of quantities t primes associated with a point P associated with a point P are said to be components are said to be the components of a second rank tensor if under a change of coordinates under a change of coordinates from a set of coordinates from a set of coordinates x2 x2 x primes, they transform according to this equation. T prime r s will be equal to del x by del x del x by del x t, and this t should be unprimed. So t I j, this is r s, so one of them should be r, another should be s. So prime r and prime j and unprimed I and unprimed S and I, primed S and primed S, or maybe one of them should not be primed. Yeah, this is unprimed. So this is the definition of tensor, right? Let me read it again. A set of quantities t primes, which are these, associated with a point P are said to be the components of a second rank tensor. There should be second order tensor, right? Second order tensor if under a change of coordinates from a set of coordinate x's to x primes, they transform according to this, right? So where this partial derivative, they are evaluated at point P. So this is the definition of tensor, and the book I will be referring to is, we already have that in Drive. So this is the definition of tensor. You can note it down. We will do some exercises on tensor. Is this clear? Does it make sense? Kishan? Is Kishan there? No, Kishan is not there. Paras?
Yes, sir.
Does it make sense?
Yes, sir.
Very good. Kritik,
Yes, sir.
understood?
Yes, sir.
Right. Who else?
Sir,
Sir?
can you explain it once more, please?
Okay, let me explain it once more. A set of quantities, t primes, which are these, associated with a point P. So let's say we have point P. Okay? Are said to be the components of a second order tensor. Right? So this will be a second order tensor. If under a change of coordinates, you are going from x's to x primes, this should be the transformation relation. Is it clear now?
Sir, it means basically tensor is a kind of a matrix type thing.
No, 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 no. I did not say matrix here.
Sir, in the second line, we are saying that it is a component of a second order tensor. Then what is actually a tensor? It is a component of tensor itself.
Tensor is a component of tensor.
Sir, in the second line, you have written it is associated with a point
Yes,
are
that point
said
is.
to be are said to be the component of a second order tensor. That I am not getting.
Oh, okay. So order we will discuss later. We will discuss later. You can note it
Okay, sir.
down. This is for your notes, right? If somebody asks the definition of tensor, this is what you have to write.
Okay, sir.
Yeah, is this clear, Namit?
Yes, sir.
Right. So it makes sense, right? Vivek, is Vivek there? Jamin, this is clear? इसको समझ लो because अगर मैं आगे बढ़ जाऊंगा then you will not be able to understand. Jamin, does it make sense? Jamin is there. I don't know. Janil,
Yes, sir. I was actually who was asking the doubt.
I say. I did not look at the screen.
Okay, sir.
Right. So Namit, it makes sense, right?
Yes, sir. Little bit.
Little bit. But to me, it does not make any sense.
Yes, sir. Actually.
Right? And this is not the way we should learn or understand anything. But the thing I found, I did a small experiment. The thing I found that most of you are afraid of saying that you did not understand. I asked you different people, say that does it make sense? Most of you said that yes, it makes sense. Because if I repeat it 4 times, and if you read it 4 times, it may give you a false impression that you have understood it. So this looks fine for taking notes, teaching in the classroom, finishing some lectures, and finishing lots of teaching stuff in 1 hour lecture and go away. But did we really understand this?
No, sir.
No,
No, sir.
neither the language, lots of jargons are there. This expression is also complicated looking. You should ask that where does it come from? Right? What is point P? Why did you say point P? What do you mean by coordinate transformation? Why do we have to talk about coordinate transformation here? Right? And finally, why this rule? What is the second order? So you have to be bold enough. You have to be courageous. You have to be shameless to learn something. Right? All these qualities a student should have. नहीं समझ में आया then we should have a courage and we should not take any shame, or even if it is a shame then we should take it because our goal is to learn it, right?
Yes, sir.
Right. So tensor is the thing which we are most of us are learning for the first time. Thanks to internet that we have come across this word, but most of us we do not know these things. So this is not how I will introduce the topic to the people who have never come across this. So I'll remove everything. This is not the way you should teach, if you should learn, rather. So let us get back to tensor and why it should be taught to physics students. Now we will talk about other things. Right. So let me try to introduce the tensor, and believe me, the first lecture is the toughest when you have to introduce some topic and you have to give the broad picture of the topic and then relate it to your curriculum and your learning. That's the challenge. Let me see. The book, I have already told you, the book I will be following what I have already shared in the Google Drive. And the name of the author, it's a big name, but let me anyway try to pronounce it. Tensor Calculus for Physicists, it is Dwight E. W-I-G-H-T. Dwight E. And the surname is the difficult one. Non Schwander. Neuen. Noan Schwander. SCH. My God. WANDER. So this is the guy. Nicely written book. I will introduce you the book also. I'll share my screen shortly. Right. So tell me, some of you might have come across this tensor. It could be first course for most of you, but some of you might have come across this word tensor. So did you read it earlier? I'm not expecting
Yes,
you
sir,
to
little bit.
clear answer. Yeah.
Yes, sir. I saw some videos on YouTube about that.
Yeah, you saw. So that is the curiosity, right? So because we are physics students, right? And we come across physical quantities, right? Because we want to quantify the things. We want to measure the things. That's the meaning of quantification. We want to put them in the numbers, right? So we have a unit for all those physical quantities: meter, kilogram, second, and so on, right? Unfortunately, we do not have the units for many things. For example, people talk about the pain, people talk about emotions, right? Care, love, patience. All these things cannot be quantified so far. Same with the IQ, intelligent quotient. People are trying to give absurd things. Willpower. So for physicists, if it is not measurable, it cannot be written, described by a symbol, or it cannot have a unit, then it does not exist for you, right? People talk about it. It is there for the arts and humanities people. They write lots of poetry on love. But for physics, it is difficult to, first of all, quantify what love is, how much one loves another one, and also, what is the definition of love? Does it really exist? What could be the unit? So those kind of things are not for us. We are interested in the quantities which we can measure, which we can observe. So there are, so far we came across the two kind of quantities: scalar and vector. So the only difference between a scalar and a vector is, what is the
The
difference?
direction. The direction.
Direction, right? Right? So, for example, tell me where do these Xavier students generally go outside the Xavier campus? कहाँ पे जाते हैं? Let me take a nearby institute. This is your St. Xavier's College. You are here, and this is, let's say, your PRL, and this is u. So if I tell you that you have to go 1 kilometer to reach PRL, is this sufficient information?
No, sir.
Sir,
No. What is missing?
direction.
Direction. Right. So there are two ways to give the direction. First way is this, a direct distance, the shortest distance and the vector along that. But we know that is not always possible unless we go take the aerial route. The other way is we can make it in two parts. I can go in this direction by some kilometer or fraction of kilometer and in this direction. So this is vector sum of this. This is one vector and this is the vector sum of the two vectors. Right? So this is another way of describing the direction. This is one way. Let's say, let me call it S, let me call it point P, and let me call some intermediate point I. So we wanted to go from S to P, so we wanted this vector, which will have unit, unit means magnitude as well as the direction. So magnitude we know 1 kilometer, and the direction we know along this direction. But this direction can be described in this way also, this and then this, or this way also. So this particular vector, particular direction can be decomposed into two mutually perpendicular directions, x and y. You have to move along x-axis, then you have to move along y-axis, right? And there could be plus x, plus y, minus y, depending upon where you choose your origin. If this is your origin, then it is a positive. So you need two directions, two vectors now. Instead of one vector, you need two vectors, which are along the direction, along the two mutually perpendicular directions or mutually orthogonal directions. They make 90-degree angle. And I'll tell you why do we talk about the orthogonal direction. It will be clear. Why they should be the 90-degree. The angle should be 90 degree. Why I cannot choose this direction? Why cannot I choose this and this? This is not, this should be my y. And this angle is less than 90 degree. Or this, where the angle is greater than 90 degree. They will not work. Only this thing will work. When the angle is exactly 90 degree. So this distance I can divide it in two parts. Okay, this is when I am moving in this plane. But if I am moving in 3 dimensions, for example, Xavier is here and PRL is out of the plane, somewhere here. Then again, I can directly point from here to the PRL, or now I will be decomposing my vector or the direction into 3 mutually perpendicular directions now. I will move along x, I will move along y, and then I will move along z also to reach PRL, if it is out of this plane. So then in addition to x, y, I will need another direction z, which is out of the plane. Right? And then all of them should be the 90 degree, and they should also follow the right hand rule. That is also right-handedness. What do I mean by that? Is this. That if this is my x direction, I will place my fingers, right hand fingers, along this x direction. Then I'll fold my fingers along y direction. I'll fold my fingers along y direction. This is x, this is y. We generally put the unit vector, but that is fine. So x, y. And then z direction should be along the direction of thumb. It should be the direction. It should be pointing along the thumb. So x, y, and z. So z will be out of plane. Z will not be inside the plane. Right? So x, y, and this will be z. I cannot choose this to be x and z, because now this y will not be out of the plane. This will be inside to the plane in order to satisfy the right hand rule. So in your book, you will not see this thing. You will see that this is sometime, when this is sometimes z, this is x, and now this is y, and so on. So they have to follow the right hand rule. The same rule is described by these three fingers also, that this should be x, this is y, and this is z. X, y, and z. Right? Why they should be at 90 degree? Can you tell me? Why we want our axis to be at 90 degree? This is very, very important thing.
So, sir, we can apply Pythagorean theorem for vector addition.
No. No, not exactly. Because it is right 90 degree, we can use the Pythagoras theorem. It is not the other way around. It is not that because we want to use the Pythagoras theorem, so we want them at 90 degree. No. Because they are at 90 degree, so they will make a right angle triangle, and we can apply the Pythagoras theorem. No, it is not other way around. Because if they are at 90 degree, then only they will become mutually independent. If the angle is less than 90 degree, then they will not be mutually independent. Why? Because this direction will be described by I and obviously some magnitude xi. This will be by j and then some magnitude y, right? How much we have to move along y. So now, if I take the dot product of I with j, so this will be I j cos 90 degree. This is 1, 1, and this will give you. So the dot product will be 0 only when this angle is 90 degree. And dot product 0 होने का मतलब क्या है? They are independent of each other, which means that this vector does not have any projection on j and vice versa, which means you cannot write I in terms of j. Let me tell you what do I mean by that. Let us replace this I and j with some other vector, arbitrary vector a and b. I have a vector a dot b. So this tells me what is the projection of a on b, isn't it?
Yes, sir.
Because I'll tell you what do I mean by that projection. I'll tell you what is that. So a dot b will be a, b, and the angle between two. Let's say that is theta. If this is finite, so if this will give you some value which is not equal to 0, then the component of one vector can be written in terms of the components of other vectors. That I will tell you. So if the dot product is non-zero, then they are not mutually independent. If it is not 0. If it is 0, then I'll say that the two quantities are mutually orthogonal because the angle will be exactly 90 degree. I want to choose the independent direction. Otherwise, they will not be mutually independent and they will not look two different directions. Then there is no point in choosing two directions. They are as good as only one. I'll tell you what do I mean by that. But this you should appreciate, that they have to be mutually orthogonal. To make a basis which is linearly independent. I'll tell you what do I mean by basis and all those things. But this, so for vector, if I have a vector A, I need these directions. So vector only does not come in one direction. It depends on your dimensionality, right, of your problem. If you are dealing with 2 dimension only, so let me write a general expression of a vector and then we will discuss other things. So a general expression of a vector is, all this we are doing for vectors, right? And then we will talk why do we need tensors. So a vector A is nothing but a magnitude and a direction. Is that correct? So a general vector in 3D is described as this: ax x plus ay y plus az z. This is the general form of a vector, and which can be written in even more generalized form is this: ax could be function of x, y, z, x. Ay could also depend on x, y, z, y, plus the third component az could also be function of x, y, z. Right? This is true when the ax, ay, az are the coefficient, they are the numbers, and this is true when they are variable, they are expressed in terms of x, y, z. So this is a vector. This is how a vector should look like. If you talk about 2D only, then you will definitely not have this one, this component. And obviously, Z dependence will not be there. So similarly, if I talk about 4-dimensional problem, 5th dimension, or maybe infinite dimensional problem, right? In quantum mechanics, we know that there are bases which have infinite dimensions. Definitely more than 3, they're higher dimensional. Depending upon that, I can have it. Right? So this vector can be described in short form like this also: ax, comma ay, comma az, within a bracket. So I take the coefficient, and this will be described in a basis of this: x, y, z. So this is my basis. 3 डायरेक्शंस. कई बार इसको ऐसे भी लिखते हैं शॉर्ट में: I going from 1 to 3. So x1, x2, x3 also they denote it. Or I going from x, y, z also. Right? So E1, E2, E3. This is the 3D basis. So in this basis, this vector will be described by these coefficients: ax, ay, az. Simple. If it is only 2D, then I will need only 2 bases: Ex and Ey. This is my basis, and Ex and Ey should be independent, which means their Ex dot Ey should be 0, and Ex dot with itself should give you 1. This is exactly the same thing. We are trying to generalize it. The same 2D or 3D geometry, we are trying to generalize it for the higher dimensions. That's it. So for example, now if I say that you have a vector, let me take an example and then I will talk about other things. So I should not remove this. In fact, I should not be removing anything, but I have to remove something. So if somebody says that in a 2D basis of E1, E2, your basis is E1, E2, and you have a vector, let's say 1, 2. So what does it mean? The vector is basically E1 plus 2E2. In the more familiar form, it is I plus 2j. This is the vector. Right? If I talk about 3D also, that if the basis is this, then it will be 0. So this is the vector. Sometimes it is also written as x plus 2y, depending upon the notation the book is using. But you should not be carried away, distracted by the notations, because we know what they are representing. They are representing the directions. Is this correct? Any questions you may have?
No, sir.
Now इसी का बात करते हैं. Let's talk about this vector. अगर 2D vector ही लेते हैं, and we do not have this component, this is fine. And you can, I know you can quickly tell me what will be the magnitude of this vector?
Root 5.
Root 5. Yes. And how do you know that?
Sir, under root of 1 square plus 2 square.
कहाँ से आता है? क्यों तुमने ऐसा किया? Why did you do that? So you said under root of 1 square plus 2 square. Why did you do that?
Dot product of vector A with A.
Very good. So this is nothing but the square root of the dot product of a vector itself is again important quantity, because this gives you the square of the length or the magnitude, because this vector A is basically a point measured from the origin, isn't it? So origin has coordinate 0, 0. So this minus 0, 0. It's a distance between this point P, which denotes this vector A, and the origin. So this gives you the length. In the same way, you can find out the length between 2 points, P and Q. This is the length. So this is the vector. You can define PQ, and you can take its dot product with itself. Take the square root to find out the length. And that will be, so this PQ will be, so OP plus PQ vector is equal to OQ. So you know the vector PQ will be OQ minus OP. And because origin always have 0, 0, so I can drop it. So this is vector Q minus vector P. Or let me denote them different vectors. So this is vector A, this is vector B. So this is vector A minus B minus vector B. If I want to construct another thing from Q to P, keep this in mind. ये बहुत use होता है electricity and magnetism में. I'll tell you how. So this vector is pointing from P to Q. From P to Q. Right? And this is how we found it out. OQ minus OP. If I want another vector pointing from Q to P, then I will take A minus B. Right? So electricity and magnetism में कहाँ use होता है? That if I have two charges, एक का position vector R1 है, एक का position vector R2 है, so there will be a force that will be acting along the line joining two charges, and the force will be equal and opposite for one charge and the other. If this is applying a force R2 on this, then R2 minus R1 will be, let's say, R21. So what does it mean? That your vector is pointing from R1 to R2, right? From this to this. So here, this minus this minus this. So your direction of vector is from R1 to R2, right? So the force will be, let me call it Q1, Q2. So it will be some constant K, Q1, Q2 divided by R12, this vector, because force is a vector. right? But we know the vector can be written as the
हेलो सर सर
Yeah.
मे बी R12 का स्क्वायर होगा ना शायद
yes, sorry, square. But now you have to put the directions. So force का direction क्या होगा? So that will be R12, this unit vector. So which force is this? Is this force on Q1 due to Q2 or it is on Q2 due to Q1? Because another force will be equal and opposite. Only the direction will change. It may be PQ will be simply minus QP. That's it. Magnitude will remain same. Only the direction will change. So here, this what is this force? F12. That is the force between two particles, two charged particles, which will be acting along the line joining them. But the direction could be this, either this or this. So how will you find it out? कौन सा direction है?
Sir, by the notations, means 1, 2 and 2, 1, there will be two notations.
So what is this? So यहाँ से clear है. 1, 2 will be pointing along this, right? R12 will be simply minus R21. So it will be pointing from Q2 to Q1. So कौन सा force है? Is it on Q1 due to Q2 or on Q2 due to Q1?
सर ऑन Q1 ड्यू टू Q2
On Q1 due to Q2, but that will depend on other things also. For example, what kind of charges they are. If the two charges are positive charged, then they will repel each other. Then what kind of force Q2 will be putting on Q1? Directed outward, right? तो उसी की वजह से तुम्हारे फोर्स का साइन भी चेंज होता है. इट इज अट्रैक्टिव फोर्स और रिपल्सिव फोर्स. That's how you choose the sign to take into account this direction of the vector. So these things are very, very simple, but the problem is we have not thought about it carefully. Gravitational force, that will always be an attractive force. So we know that on one particle it will be always to this, another particle it will be to this. So that then it is clear. But for charges, we know that depending upon the nature of the charges, the direction of force could be different. Right? So you can think about this. You have sufficient material here. So this dot product is very, very important. You will see in the special relativity that tells you the length. And that length is a scalar and which remains invariant under the coordinate transformation. I'll tell you what do I mean by coordinate transformation and why it is important to talk about them. Why it is important to define a vector and the tensor and so on. Coordinate transformation. And this length, dot product, is important. All right. So whatever we are talking about is about the Cartesian coordinate system. Cartesian coordinate system. One last thing I want to tell you is the direction cosines. So basically, I will again write my vector. Vector A is, let's say, xi plus yj plus zk, and xyz, they can have any value. They could be, depending upon my problem, they could be either integers, they could be fractions, right? They could be real numbers, they could be complex numbers also, right? If you're talking about quantum mechanics, we will be dealing with the complex numbers. All right. So x, y, z, depending upon the range they may have, they can take any value. All right. So what is this? Basically x. I'll take the vector A and I'll take its dot product with I. What will I get?
X.
X. So projection of this vector, let me remove the two vectors. This is the point P. So vector can also be represented by point P. So it is basically the the position vector of that point P, right? And it can have some coordinate, let's say 1, 2. So this is the vector. So how will you get this vector? 1i minus 0i, 2i minus this. So that is the difference between this point and this point, right? And you know this is always origin, so you don't have to do anything here. For example, if I want to know the coordinates of this point Q with respect to P, then obviously I will do this minus this I and then J, right? So you can find out the coordinate of a point with respect to origin and with respect to any other point also, right? In classical mechanics, we do that. If we have a system of particles, if we have a rigid body, then we can define its coordinate either with respect to the origin, the space fixed coordinate, or its coordinate with respect to the center of mass. All right, fine. So this is the projection I. So projection का मतलब ये है. This is basically x. This length is x, which is this a dot I. And I want to use a dot I का definition of the vector dot product of the two vectors. Cos theta, right? So this is basically magnitude of A is A, magnitude of I is 1, and this cos theta. So this A dot I equal to x is this A cos theta. So x is A cos theta, right? This x is A cos theta, theta being this angle. What I can further simplify it, I can write vector A divided by magnitude dot I is equal to cos theta. So cos theta is nothing but the dot product of direction A and direction I. So this is also important quantity. इसको हम बोलते हैं direction cosine, because we are taking the cosine of this angle. So this will tell me what is the inclination of vector A with respect to direction x. Similarly, I can take A dot J is equal to, so what angle vector A is making with J, and that will come out to be cos of, because this is phi theta, this could be phi, and A dot K, that will be the orientation of vector A along direction K. So this is a unit vector. We divided it by the magnitude. This will come out to be psi, right? So these are the direction cosines, which are also useful when you will do the rigid body dynamics and other things. These things will come across. Similarly, its projection along y direction will be this vector A dot J. That will be the cos of this angle. You have to find out this angle and its orient. Yes? Was there any question?
No, sir.
Okay, all right. So this is the way. Now let us talk about the need of coordinate transformation and how do we get the definition of a vector under the coordinate transformation. Any questions from these definitions?
No, sir.
Right. That's great. Because we are talking about the dot product, we will talk about the cross product also. And then we will start discussing the tensors. So, right. Before coming to the coordinate transformation, we need to refresh other things again. So, A dot B. This can be written as vector A, AXI plus AY. I am used to this Y and J. dot bxi plus byj plus. So these are the two vectors in their component form. Now let us see the dot product. So ax with ax will give you ax bx, ay by plus az bz. This is a dot b. Projection of vector a on vector b, and we know that this is same as b dot a. That is for the coordinate system we are talking about, Cartesian coordinate system. Right? Now another important thing, interesting thing we can introduce is now the indices. This whole thing can be written in a short form like this. Sigma I, instead of x, y, z, if I use a1, a2, a3, then it will be even better. So this I will write a1, b1 plus a2, b2 plus a3, b3. So I can write them as sum over 1, 2, 3, sum over I, 1 from 1 to 3, ai, bi. Is that correct? So the dot product can be written in the indices form like this. Is this clear?
Yes, sir.
And we can use the summation convention also now. Summation convention says that if the indices are being repeated, here is I, here is also I have I, then sum is implied, right? Even if I do not put it, that means that it will be summed. All the repeated indices will be summed over. Right? So the sum implies. If I write it this or without, with sigma or without sigma, the summation is implied. That's a summation convention used by Einstein for the first time. So we can remove that sigma and i's and also we can write it. Because the indices are being repeated ai, bi, then we will sum over all the i's. So I will run from 1 to 3. So there will be a1, b1, a2, b2, a3. If it is something like this, ai, bj, now the indices are not repeated. I and j are the different indices. Now summation will not imply. We do not need to sum. Right? So these are just one of the possible combination of the multiplication of two vectors. One component and another component. One component of A, another component of B. They could be same, they may not be same. I'll tell you the Kronecker delta function also, but not now, later. All right. So this is A dot B. Let us talk about A cross B. You can verify this thing because I dot I will only remain. I dot J, I dot K, similarly the other terms will be 0. Let us talk about A cross B. So unlike the dot product, it is called as the vector product also, cross product. And the output of, and the resultant is a vector. The vector is like this. Magnitude of A, magnitude of B, sine of the angle between two, and a direction n. So this is the direction normal to both A and B. Right? So this is the magnitude and this is the direction. All right. So how will I find out A cross B? Again, I will write vector A, AXI plus AYJ plus AZK cross BXI plus BYJ plus BZK. I want to write this also in the indices form. You know, there are various ways to find out this cross product. Right? People make this determinant also I, J, K, the component of first vector AX, AY, AZ, component of the second vector BX, BY, BZ. and then find out the determinant of this, right? Right. Or there are other things. So this will be a vector now, and the components of this vector will be A cross B. If I want to know the x component, there are other rules also. The A cross B, I want to have x component, so I will take yz minus zy. How do we do that? So this is x, so y component of A, ay into bz minus az into by. This should be the answer. Similarly, I can have y and z components and so on. And this can be written as, so the A cross B, the ith component will be written as, so if this is I, so it will be written as sigma or epsilon ijk, not sigma, it is epsilon ijk, and then aj bk. This is the cross product in the indices form. So this is known as the Levi-Civita symbol. And this has this property. Sigma ijk, they could be +1, they could be -1, or they could be 0. When will they be +1? +1 तब होगा when they are in the cyclic order. Cyclic. It will be -1 when it is non-cyclic. And it will be 0 when 2 or 3 indices are same, any 2. This is known as the Levi, whatever, Civita symbol. And from here, I would like to introduce you the tensors and the coordinate transformations, etc., etc., etc. So using this property, I can write down this cross product very easily now. I don't have to use the determinant of this simple thing. So be careful now. This is just an exercise, practice exercise. So you should participate. A cross B, I is vector ka. A cross B is a vector. I am taking its component, ith component. This will be I, J, K, B, J, sorry, A, J, B, K. So repeated in this index कौन सा है यहाँ पे? कौन सा इंडेक्स रिपीट हो रहा है इधर?
J and K.
J and K, very good. On this side, J and K are repeated index. So we need to sum over them, right? Indices. Indices is the plural for index, right? So let's find it out. So, and the sum will be over 1, 2, 3. So I, J, K, they all are running from 1, 2, 3. So let us take the x component. A cross B ka first component, x component, will be epsilon, this will remain 1, and then jk, aj, bk. And now we know the j and k will be summed over. So what will I get now? Let me run over j first, and then we will run over k, or vice versa. Let me take j equal to 1 first. So epsilon 1, j is 1, k is 1. So this will be a1, b1. Plus I will remain 1, J, I will keep 1 again. I'll change K to 2. A1, B2. And then K ka third value, 1, 1, 3. A1, B3. So there will be 9 components. And I'll show you that this is a kind of tensor. I'll tell you why. Plus, now 1 will remain same. I will take J to be 1 now. And I will run over K. 1, 2, 3. A2, B1. A2, B2. A2, B3. Finally, I will choose J to be 3. These are the 9 components, 9 terms. And I know when the index are repeated, so यहाँ पे sub index repeat हो रहा है, this will be 0, this is 0, this is also 0, 1 2 1 repeated 0, 1 2 2 0, 1 2 3. So this will give you 1 because they are in the cyclic order 1 2 3. So you will put plus 1 here. All right. 1 3 1 repeated, 1 is repeated. 1 3 2, yes, nothing is repeated, but they are not in cyclic order because 1 2 3 1 2 3 1 2 3. So 1 2 3 or 3 1 2 or 2 3 1, they will be in cycle. But 1 3 2, so 1 and then 3 and 2, so they are not cyclic, so I will put minus 1 here. 1 3 3 is 0. So I am left with only 2 terms, A2 B3 minus A3 B2. That's the component for you. So this is how you can write the vectors and their dot and cross product in the indices form. If you want to write a vector A in the index form, then it will be simply AI, EI, right? And it will be repeated over all of them. Now, because when we will talk about coordinate transformation, we will be introducing the notion of matrices. Matrices, I don't know. Matrices, I call them matrices. So, how we can denote a vector into the matrix? If I have a vector A, how can I write this in the matrix form? Can you tell me? I want to write a vector in the matrix form. How can I write that? And everything will become so smooth from here. So this is A, this is B, B can also be written as Bj, Ij, another index because I have already used. If I want to find out A dot B, it will be AI dot Bj, Ej, and these are the constant, they will come out. So AI Bj, and I will get AI dot Ej, right? The dot product of the directions, and we know the dot product will be basically give you AI Bj delta Ij, Kronecker delta. So if this is same, for example, I dot I, it will give you 1. If it is I dot j, it will give you 0. So that's the property of Kronecker delta function. Delta Ij is 1 or 0. I when 1 when I equal to j, and 0 when I not equal to j. So that is another way. And I know I'll get it to be AI Bi. The same result I obtained from multiplying the component wise. Yes, so last thing, last 5 minutes. How can I denote a vector in matrix?
Components in row matrix and basis in column matrix.
Component in
Row matrix.
components in row matrix. So row matrix means there will be only one row, right?
Yes, one row.
One row. All right. So AX, AY, and AZ. And then,
Basis in column matrix. EI, EJ, and EI, EJ, and EK.
okay, let me call it EX, EY, and EJ, right?
Yes.
Okay. Tell me what is the dimension of this second matrix?
Three,
इसमें
which
कितने
is 3
कॉलम है?
by 1.
कितने कॉलम है इसमें?
One column.
वन कॉलम. और कितनी रोज
3
हैं?
row. 3.
इसमें कितने कॉलम्स हैं?
3 columns.
3 कॉलम्स. और रोज कितनी हैं?
1.
कैन यू मल्टीप्लाई द टू?
सर आपने गलत लिखा ना. रो बाय कॉलम होता है.
Yeah, so
One
how
row.
many rows are there? One row, 3 columns, right?
Yes, but in basis.
Acha. So 3 rows and 1 column. Right? So what will be the resultant?
AX, EX cap plus AY, EJ, EY cap plus AZ, EJ cap.
Yeah, so resultant will be
1 cross 1.
1 cross 1, right? And that is exactly AX, EX plus AY. That is fine, right? So this is one vector in one basis. I can choose another vector in another basis, but we will talk about the different bases, not for now. We will say that we are going to use the same basis for all the vectors. So I do not need to do this, use this. Is that fine? Because this will remain same for all the vectors. Only the components will change. So I have vector A, I have another vector B. That will be Bx, By, and Bz. This is also 1 cross 3. I want to know the A dot B. How will I get that? From these matrix forms. So what A dot B will give me? This will give me a scalar, a number, something like 1 cross 1. I'll put this matrix 1 cross 3 matrix and 1 cross 3 matrix. First of all, it cannot be multiplied. So what I need to do now, I need to take the transpose of one of them. Right?
Yes.
Because I'm not going to touch my basis, so I can play around with these things. I can put them either in a row or in a column matrix. That freedom I have. So one of them should be kept as the row matrix. Which one? This one or this one?
A in row, B in column.
So A in row and B in column. So this will give me 1 cross 3 and 3 cross 1, right?
Yes.
So I will take transpose of this. And this will come like this. Bx, By, Bz. Right? This is how I take the dot product of the two matrices or the vectors. So depending upon the notion you are choosing, so you can write it as A transpose B or AB transpose. If you're defining your vector, generally this is the notion. You denote the vectors as a column matrix. So generally, in the books also, the convention has been that this is the vector and this is the transpose of the vector, which will be a row matrix. So A dot B into B will give you the dot product. Right?
Yes.
Similarly, what about the cross product? Or what about the multiplication of two matrices simply? Simple multiplication. A and B. A into B. So that means that this is AX, AY, AC. So direct, what is the dimension of this?
3
cross.
3 by 1.
And this is also 3 cross 1. So you cannot definitely multiply them, but you can also multiply them in such a way to get the 3 cross 3 matrix. वो भी कर सकते हैं ना?
Yes.
उसके लिए क्या करना पड़ेगा ना?
Cross product.
No, not cross product. Cross की बात नहीं करेंगे. So this is 3 cross.
Transpose of B.
So this should be made at 1 cross 3, right? So now this one should be the row. So in this form, so this is basically AB transpose, isn't it? And this will come out to be a 3 cross 3 matrix. Isn't it right? And what will be the element of this matrix? This will be first row multiplied by first column. So it will have AX, BX, then AX,
X,
BY,
BY.
AX.
BZ.
So this element of this matrix will have all the possible combination of AX and A and B, components of A and B. AX, AY, AZ, let me write them. AY, BX, AY, BY, AY, BC. And this will give me the idea of tensor. यहाँ से हम लोग डिस्कस करना शुरू करेंगे. What a tensor it is, why do we need tensors, right? What do we mean by? So it is, you can see that this is a product of two vectors. That should be the first definition of tensor for you. Not the scalar product, because for a scalar product you will take A transpose B. But here you are doing A B transpose. Right? But that is another possibility of multiplication. And this will result, this is a tensor. I'll tell you why it is a tensor, why we need, what do they represent, and then we will discuss the tensor algebra and obviously the tensor calculus also. So we will need to take their derivatives also sometimes. But this we are only talking about the tensors in or the vectors in Cartesian coordinates. We need to do the coordinate transformation. We need to move from one coordinate system to another coordinate system, right? Can you give me the examples? I may need to move from a 2D Cartesian coordinate system to r theta. I may need to move from 3D Cartesian coordinate to 3D spherical polar coordinate also. And then I need to find out the relation between the old coordinates and the new coordinates. And then with that, I am ready to define all the quantities which were function of the old coordinates in terms of the new coordinates. Any function which was known in this coordinate system, I will be able to find out the same function in now new coordinates using the coordinate transformation. But why do we need coordinate transformation? We are not discussing any mathematics now, simple things. Give me some examples in physics where we do the coordinate system. We cannot live without doing the coordinate transformation.
एग्जाम्पल सर, अगर एक कोई बॉल है कि वो स्फेरिकल सरफेस पे मूव कर रहा है, देन वी ओनली हैव टू take care about theta and phi because r is already constant. But if we work in Cartesian coordinate system, then we have to worry about x, y, and z, all the three components.
Very good. Very good, Vivek. तुम्हारा BSc कहाँ से था?
MS University, Baroda.
I see. Right. So Vivek gave the right answer. He said that when the constants are there, when the motions are constrained, when there are restrictions on the motion, For example, if a particle is moving along the surface of the ball, of a sphere, it is not allowed to go inside the ball, right? So it's r, it is always going to be r distance from the center. It is only changing the theta and phi. So if you do the coordinate transformation from x, y, z to r theta phi, then you can basically reduce your coordinates. You do not need to treat r as the coordinates because that is the constant always. You only need to solve your problems in 2D now, theta and phi. So in constrained motion, in classical mechanics, we talked a lot about this, that we do the coordinate transformation. So we choose the suitable coordinate system to solve our problem. For example, simple pendulum. In pendulum also, you do not need x and y, even if the motion is 2D, because r, the length of the pendulum, or distance or the position of the particle from the origin is going to be fixed. R is always going to be L, length of the pendulum. So the only coordinate you have to worry about is the theta. So its polar coordinates are more suitable to solve the simple pendulum problem compared to the Cartesian coordinate system. Yes, hydrogen atom problem also, right? We can take the spherical polar coordinates, and we know from the quantum mechanics and other things that the distance between the electrons is going to be fixed from the nucleus. You don't have to worry about the r. You only have to take the theta and phi into account. This is one example. There are other examples also. Tell me. I can give you the hint. Special relativity. There also we need to do the coordinate transformation because we have one reference frame which is at rest. We have another reference frame which is moving at some constant velocity. We want to measure we have measured the coordinates with respect to this frame. We want to measure its coordinate with respect to this frame. So that we can do by using the coordinate transformation. We can relate the coordinates of this frame with this using a transformation relation. Right?
Yes.
Transformation relations are basically you can write the coordinates of one system in the terms of the other system. One last example and then I'll leave you. In cosmology also, we want to know how fast some object might be moving, right? We can do the coordinate transformation calculation to find out the speed by which the object is approaching us or it is going away from us. Maybe similar calculations are used to find out the expansion rate of the universe. So we need to do the coordinate transformation. And what are the rules that vectors follow for the coordinate transformation? We will first learn that. So that is the definition of vector, mathematical definition of vector. And then we will see what will be the definition of tensors. So the first definition I wrote was basically the transformation rule for the tensors, right? And we know the vector is that there's some relation between the scalars and vectors, something like this. That if I'm talking about 3D basis, then the scalar only need 1 point and the vector needs 3 values. If I want to generalize it, so I can say that it is something like this. Dimensionality to the power 0. So 3 is the dimensions, to the power 0 is the rank, let's say. So 3 to the power 0 is 1, so vector is something of rank 0. Sorry, scalar is something of rank 0. Vector is 3 to the power 1, which is 3. It is some quantity of rank 1. So similarly, we can assume that there should be quantities with higher ranks. 3 to the power 2, 3 to the power 3, 3 to the power 4, and so on. So this is how we will generalize our understanding of the vector to understand the tensor. That a scalar is a tensor of rank 0, dimensionality raised by the rank. The dimensionality could be 2. If we have 2 dimensions, then the vector will need 2 components, 2 to the power 1, right? X and Y coordinates. If the dimensionality is 4, for example, spatial relativity, then any point needs to be described by the 4 points, X, Y, Z, and the time also. That is the event for you. All right, if there are no more questions, comments, and thank you very much. I'll see you on Thursday. Bye-bye.
Bye, sir.